or dynamic binary translation. Static binary translation takes the binary, writes out the assembly code of the binary, does some instrumentation on the assembly code, and then assembles it back into a new binary. This has the drawbacks that maybe not all code can be found due to obfuscating or, well, jumping into an instruction that is very prone, where the Intel instruction set is very prone to. And it also has some other drawbacks. It has a slight advantage in speed, as it doesn't have the additional translation overhead that dynamic binary translation incurs. But overall, it doesn't work out for security. Dynamic BT, on the other hand, translates all code as it is being executed. Right before we would start, or we would jump into a basic block, we translate that basic block, place it into a code cache, validate everything based on our translation tables, and then let the program execute that newly translated code. So in user space, if you have the binary translator running, we have 2 levels of code execution instead of just one. Normally in user space, all code is the same, but through this binary translation, we kind of implement 2 levels of code execution. The first level is the privileged level of the BT library. This part of code can execute any instruction and is precompiled and can also execute any system call, and this is all unchecked. And on the other hand, we have a code cache where we place the translated user code in. And all code in that code cache is kind of checked and validated, so it doesn't execute any unintended system calls and always will go through the system call interposition framework. But the user space program always believes that it is running in its original code layout, and it doesn't even see that it is being translated or doesn't have any pointers into the code cache, so you cannot change any instructions there or jump into an instruction to execute some malicious code beneath the binary translator. So using the binary translator, the program is encapsulated in an additional protection layer around the system. So all instructions that we execute are checked and validated. We have a checker that goes through all direct and indirect jumps and verifies the targets of these jumps for both direct and indirect. This is important later on. We only branch to targets that are on the instruction at an instruction start, and will make it not possible to branch into instructions. And we'll also verify all locations where system calls are executed and limit these locations. So to give you a little bit a bigger picture about that, this is what binary translator or binary translation looks in a nutshell. On the left-hand side, we've got the original program with all its basic blocks. And normally, if the program is executed without binary translation, the execution flow always stays in that graph. It branches from one basic block to another and always stays in that control flow graph. But if we have, or if we add binary translation, we have a translator that uses opcode tables which define the complete IA32 instruction set and translate basic blocks and place these basic blocks in the code cache. The translator always works on a basic block level and just parses a basic block and passes it into the code cache. The code cache contains these translated basic blocks, but only the translated one. The binary translator uses a mapping table which maps between locations in the original program and locations in the code cache. So whenever we have an indirect jump going to a specific location in the original program, the binary translator will fall back to the mapping table, look up the mapping to the corresponding entry in the code cache, and redirect execution flow to the code cache back. And the execution can continue in there. If you have a direct jump, an unconditional direct jump, then we can fix the pointer into in the code cache and emit a specific location in the code cache without sacrificing or giving out too much information. If a basic block is not yet translated, we construct, or if we are translating basic block number 3, for example, we see that it has 2 outgoing edges. One of these outgoing edges points back to basic block number 2, and the other outgoing edge points to basic block number 4 in the original program. So, as we translated basic block number 3, we saw that basic block number 2 is already translated, fixed that pointer, and everything is well done. But for the basic block number 4, this is not already translated, but we don't want to do too much look ahead and, well, execute too much code or translate too much code. So we just generate the trampoline that will start the translator if we go along that path. So if we are in basic block 3 prime in the code cache, and we would execute basic block number 4, this will start the translator, which will then translate basic block number 4 and place that one in the code cache. So that execution will always stay in there, or the program execution will always stay in there in the code cache. So much about the basic translator. This is kind of how binary translation looks like, and we can already guard and translate all different instructions. Now the problem is, if we implement such a basic translator, this will be really, really slow, and we'll have like a 10 to 20 times overhead. So we are really desperate for some optimizations to make the code fast. Because, well, security is good, but who will ever use this user-space virtualization if you have like a 10 times overhead? So let's start with the optimizations. There are 2 different takes on optimizations. One of them is translation efficiency to generate the code. So the compiler or the translator must be fast, as well as the efficiency of generated code. The code that we generate in the code cache must be fast as well. For the translation efficiency, we want a fast table-based translation process. So we don't have any IR-based compilation overhead, and well, for IR-based compilation, we also don't know how long the compiler will take. So it's not really bounded, or, well, it can take longer than for a table-based approach. And for the efficiency of generated code, it is very important that we master control flow transfers. These are the instructions which incur the highest overhead. And these are indirect jumps, indirect calls, and function returns. And we will discuss these things in more details later on. For translation efficiency, there are 2 approaches to build a binary translator. One of these is a table-based iterator, which has some instruction tables in the background, and the other one is based on intermediate representation, like a traditional compiler approach. The table-based iterator has no global state or intermediate representation that it needs. All instructions are decoded according to the information in these translation tables, and we just follow from 1 byte in the instruction in the code. We just follow the tables and can decode the instruction like that, and then translate it according to a specific action function that is defined in these tables. But we still have the possibility to do local peephole optimizations like inlining, as it is implemented in secuBT. And inlining already reduces sometimes more than 60% of the overhead. On the other hand, the other approach would be based on intermediate representation, more like compiler-like. And there are specific applications which do this, like PIN from Intel, or even some other binary translators. But they all need IR transformation in a kind of a global state. But they can do more thorough optimizations that they do based on the intermediate representation. They take the machine code, generate an IR, do some optimizations on that IR, maybe even register reallocating, code reordering, code restructuring, and then transform the IR back to machine code and put that code into a code cache and execute that later on. but this takes